Alright, so this will be the second video over chapter 7. So in this one we'll look at the stabilities of alkenes. So there's two main things that affect the stability of an alkene. So one is whether it's cis or trans, so that's a steric effect, or sometimes called a van der Waals strain. And then the second will be the degree of substitution, and that's an electronic effect. So if we take these alkenes, for example, these 6 alkenes, if we want to classify them, so this would be an unsubstituted alkene. Right, this alkene would be said to be monosubstituted. Right, because that's the double bond, and the double bond has one carbon attached to it, so it's monosubstituted. So for this alkene and this alkene, so they have 2 carbons attached to them. So this would be a disubstituted. Of course, that one is cis, and this would be disubstituted. So this one will be cis, and this one will be trans. And so in general, cis double bonds are less stable than trans double bonds because these 2 methyl groups are somewhat close in space. So whereas here they're very far from each other in space, so there's some steric strain here. So in general, cis double bonds are less stable than trans double bonds. And then this alkene and this one, so this alkene has 3 carbons attached, so it's trisubstituted. And this one has 4 carbons attached, so it's tetra. And so the general order of stabilities of alkenes is that trans is more stable than cis, and tetra is more stable than tri, which is more stable than di, which is more stable than mono, which is more stable than unsubstituted. So the more carbons on the double bond, the more stable the double bond is, and the less reactive it is in general. So how can you determine this experimentally? So one thing that can be done is, so if we take these 4 alkenes, they are all C4, 3, 4, 5, 6, 7, 8, they are all C4H8. So same number of carbons, same number of hydrogens, they're regioisomers of each other, or they're constitutional isomers of each other. So if we did a reaction where they produced all the same product, so then you can compare the stabilities of them. So that reaction in this case would be, for example, what's known as a hydrogenation. This will be a reaction we look at in the next chapter. So if you take an alkene, react it with H2 gas and palladium metal as a catalyst, then what this does is it adds hydrogen and hydrogen across the double bond. So basically you get rid of the double bond and now you have an alkane. So if you did that, so this is 1-butene, right? Or but-1ene, and then that would make butane. And this is cis but-2ene and trans but-2ene. And if you add hydrogen and hydrogen across the double bond, you make butane and you make butane. So the product is all the same, but the starting material is different. So if we looked at that on the energy reaction coordinate diagram, so they all go to butane, so they all go to the same product. So they all end at the same place, but they don't all start at the same place. And so what you can do then is look at the energy of this reaction, or the heat. So if you remember what delta H is, the enthalpy. So look at the heat change in the reaction, and since they all end at the same spot but don't start at the same spot, then they'll give off different heats of reaction when you do this hydrogenation. So the 1-butene gives off 2,717 kilojoules per mole of alkene. The cis-2-butene gives off 2710 kilojoules per mole, and the trans-2-butene gives off 2707 kilojoules per mole. So the one that gives off the least energy is the most stable. So this would be the least amount of energy, so that's the most stable. So least energy given off equals most stable. And the most energy given off is the 1-butene. So what this basically illustrates is the trans-2-butene is disubstituted, and the cis-2-butene is disubstituted, but one is trans, one is cis, so the trans gives off less energy than the cis, so the trans is more stable. And the 2 butenes are disubstituted, whereas the 1-butene is monosubstituted, so the 2 disubstituted alkenes give off less energy than the monosubstituted alkene, so disubstituted alkenes are therefore more stable than monosubstituted alkenes. Okay, so let's practice that. So let's take these alkenes and classify them. So are they unsubstituted, mono, di, tri, or tetrasubstituted? Okay, so the alkene on the left, so that is the alkene, and how many carbons are attached to it? So that carbon, and that one, so this would be a tri-substituted. And the alkene on the right, that's the double bond. How many carbons are attached to it? So that carbon, that one, and that one, so this would be tetrasubstituted. Okay, so another way that you may see a question like this asked, so we can more practice. So let's circle the more stable alkene in each pair. So where you'd want to start is classify them. Are they mono, di, tri, tetrasubstituted, for example? So this alkene has 2 carbons attached to it, so this is di. And that's the alkene with 1, 2, 3 carbons attached, so this is tri. So circle the more stable, so that's the more stable. Okay, so this one, there's the alkene, which has 2 carbons, so this is di. There's the alkene, which has 1, 2, 3 carbons attached, so that's tri, so that's the more stable. Okay, here, the alkene is there, 1, 2, 3, 4 carbons attached to it, so that's tetra. The alkene is there with 1, 2, 3, 4 carbons attached to it, so it's tri, so this is more stable. Okay, for this one, that's 1, 2, 3 tri. And alkene is there, that's 1, 2, 3 tri. Okay, so what to do now? So are those equal in stability? And the answer is no. So what is different about these alkenes is, so if we split that, that's priority 1 and 2. That's priority 1 and 2. So this is a trans isomer. And if we split that, that's 1 and 2. That's 1 and 2. This is a cis isomer. So these are just stereoisomers of each other, not constitutional isomers. And so, of course, the trans is more stable than the cis, so that would be the one that's more stable. All right, so hopefully that made sense, and we'll stop there.